Okay, hi everyone. Welcome to the last lecture of the week. Just a few quick reminders. So I believe your labs became available yesterday. So you have 1 week to complete them. I believe, if I recall correctly, they are due next Wednesday, I think at midnight. So I guess that's slightly over 1 week. It's 1 week and a few hours, but that's not the point. So please make sure you slowly work on that. In relation to the lab, Gideon has office hours on Monday afternoon. He posted a Zoom link, I think in the announcements earlier this week. So, you know, whenever you find some time, you can slowly work on the lab yesterday, today, tomorrow, over the weekend, whatever. And then hopefully by Monday, if you have any outstanding questions about calculations or interpretation or typos or whatever, you can drop into Gideon's office hours on Monday through Zoom and, get some help that way. And of course, you can always email your TAs for lab help and or myself for lab help as well. So there's lots of instances to clarify any misconceptions about the lab. And also as a reminder, tomorrow is I believe the due date for the first, actually, you know what, I should probably quickly, show the schedule. So tomorrow, I believe, is the due date for the first assignment. Where's the schedule here? All right. Yeah, so there we go. Today's the 16th. Tomorrow will be the 17th. So tomorrow is your due date for assignment 1. Please, it's very important that the deadline is met properly. I know students don't always think it's a big deal. I'm only half an hour late, blah, blah, blah. Ultimately, you're probably right. It's not a big deal, and especially if you're a few minutes late, 1 or 2 minutes late. But, when we were in person, and let's say you had to hand in an assignment at the beginning of tutorial, it was understood that if you walk into tutorial halfway through the tutorial with your assignment, it wouldn't, that would not be okay. That would be considered something to be late, for instance. And it is important that we sort of strive to adhere to due dates. And I know academia is a little bit arbitrary. Like, could it have been due a few hours later? I mean, maybe, but due dates are a fact of a professional life, having a career, having a job, meeting due dates. So, it's sort of important that we learn to, set deadlines for ourselves and learn how to meet them and uphold certain responsibilities in our own lives as well. So, there's more to deadlines than just us imposing the deadlines, Just a little word of advice: instead of waiting until at the last few minutes before the deadline, you should always try to upload or get things finished sufficiently before the deadline, and then that way there's time left to deal with any unforeseen issues. Unforeseen issues in this case could be like technology issues. Your internet is wonky, Canvas decides to do something weird. If you wait until like the last 3 minutes, it's your prerogative to wait until the last 3 minutes. You're absolutely entitled to do so. But that doesn't allow for a lot of wiggle room in case something goes wrong. And in the professional world, that wouldn't last. You might get away with it once or twice in the professional world, but your boss is not going to like, having to always accommodate you not adhering by the deadline, So it's always better to try to submit even 30 minutes in advance, more preferably maybe an hour in advance. And then that way, if anything happens, you can reach out to me, you can email me, and then we can sort it out before the deadline, So anyway, that's all I'm saying there. Your lab will be due on the 22nd, and of course we have our first midterm on the 24th. As you can see in the schedule here, the content of the first midterm is going to be everything electro. So that's electrostatics and that's electrodynamics. So that's all of the charge stuff, the induction stuff, induction meaning like charge separation and creating charged objects from neutral objects. Gauss's law, Coulomb's law, the parallel plate capacitor, the electric force, the electric energy, the voltage, capacitance, circuits, everything we did yesterday, everything we're going to do today, You know, so like all of that is electrostatics and electrodynamics, and all of that is fair game for the upcoming test on Friday. Okay, enough of the announcements. Let's go back to, there we go, let's go back to the notes. So as promised, we're going to do some review problems pertaining to yesterday's material, just to sort of refresh it and to solidify it now that you've had a sort of night to sleep on the material. Oh, my voice is a little bit hoarse. Okay, so this question here, oh, of course, one note is frozen again. There we go. This question here is taken from the 2018 midterm that is, I believe, already posted on Canvas. So everyone has access to this question. It's one of the short answer questions. It's not a full solution question. It's one of the short answer questions on the midterm. So I just want to show you kind of how a past midterm is pertinent to the lecture material, and how short the answer for a short answer question is designed to be. So here, the figure below shows a circuit section of 4 different air-filled capacitors. Air-filled meaning there's no dielectric inputted in them. Air-filled literally means that the epsilon is equal to epsilon naught. That's what the word air-filled means. And they're connected to an unknown larger circuit. It's not shown because it's not important. Also, we haven't got there yet. This lecture today is analyzing circuits as a whole, so we're not quite there yet. So that's why I'm doing this question. Accompanying the figure of capacitors are graphs of the electric potential V as a function of X. So you see here it's V as a function of X for each branch. Now, what does it mean for each branch? You see here that the circuit, it comes in. I don't know what goes on over here. I don't know what goes on over here. It doesn't matter. But for each branch, it means you go up here, you go up here. It means these things, according to this, are in parallel. There's 2 branches, and each branch is in parallel to one another. And then we're given some information. We know that the capacitance of capacitor 3 is equal to 0.8 microfarads. And given all the other information in the figure, determine the capacitances of capacitors 1 and capacitors 2. So this is, there's a lot, but also not a lot going on in this question. Once you kind of realize what's happening, there's not a lot to it. So as I mentioned, or as the question mentions, but as I outlined, there are 2 branches to this circuit. This means you can either go up or you can go down. So if I had to write this perhaps a little bit differently, maybe in a way that is more quote unquote textbook, it would look something like this. So this is in parallel. Now, things that are in parallel, as we discussed yesterday, will exhibit the same potential difference between point A and point B. So this tells me that the potential difference across this, what is this, capacitor 4? This tells me that the potential difference across capacitor 4 is VAB, whatever VAB happens to be. And the potential difference across all 3 of these capacitors is going to be VAB. Now, if we look back at the figure, we see here that the potential difference across capacitor 4 is, it drops from 12 volts down to 0 volts, which tells me VAB is equal to 12 volts, which means the sum of the voltage drops of each of the 1, 2, 3 capacitors has to be 12 volts. Okay, well, that could be anything. It could be, 1, 1, and 10, right? For instance, like lots of different combinations equal 12. Now, if we look at more parts of the graph, we actually have some more information. We see here that the voltage drop of 1 seems to be 2 volts. And we see that the voltage drop of 2 seems to be 5 volts. Well, that's helpful because we know the sum of the 3 has to equal 12. So 5 and 2 is 7, which means the voltage drop across 3 has to equal 7 volts. So that's really the key to this entire problem. Now that we have 7 volts, we see, okay, well, what do we actually ask for? I'm just getting excited that I'm getting somewhere in the question. So before I kind of aimlessly meander through a a dark room. Let's just go back and read what we need. We need the capacitances of capacitors 1 and 2. Well, we don't need the capacitance for capacitor 3 because they tell us that. So I know the voltage across capacitor 3 is 7 volts. I know the capacitor capacitance 3 is 0.8 microfarads. That's pretty cool. And we are asked to find the capacitance of 2 and the capacitance of 1. All right, so now I'm getting somewhere. I have a direction, I have a goal in mind. I kind of know where I need to walk towards. So now I'm thinking, okay, I know the voltage and the capacitance of 3. How does that help me relate information to the other capacitors? I also know the voltages of the other capacitors, so that's helpful. I know V2 is 5, and I know, oh, sorry, this isn't 7, this is 5. I'm thinking 5 plus 2 is 7. It is 7, but that doesn't make V3 7. It makes V3 5, because 12 minus 7 is 5. My apologies. Okay, anyway, here, we also know V1 is 2 volts. So I think to myself, what relates these things together? Well, yesterday we talked about when a capacitor is in series, we know the thing that governs them. Oh wait, no, positives are red. Positives are always red. And negatives are blue. So we know whatever charge is on one plate has to be exactly the same as the charge on the other plate. Conservation of charge. If you're inducing, let's say, +4 charge on one plate, then those 4 positives are only able to attract 4 negatives, right? So there has to be that sort of balance. So if you're stealing 4 negatives for the left side of this center part, then you have to leave 4 positives on the right side, which will in turn induce 4 negatives on this side, which will induce 4 positives on this side, which will mean there are 4 negatives on this side. Okay, so the whole point here is what I'm saying is conservation of charge. The thing that connects these capacitors together is conservation of charge. The charge on one capacitor is the same as the charge on the other capacitor. So now that I figured that out, now that I know it's the charge that sort of makes these two things relatable, I say, okay, well, the charge on capacitor 3 is going to be the same as the charge on capacitor 2. How do you find the charge on a capacitor? CV. So this is going to be C3V3 equals C2V2. And luckily we have the capacitance of 3 and we have the capacitance, sorry, and we have the voltage of 3. So we have C3 and V3 and we have V2, so we can easily find C2. C2 is going to be C3 over C2. Oh, my pen is going wonky. C2 over times V3. So this is going to be 0.8. Oh, sorry, this is V2. There we go. 0.8 microfarads, so times 10 to the minus 6, times V3 is 5, V2 is 5, so C2 is also 0.8 times 10 to the minus 6 farads. And C1 is done in a very similar way. We say the charge on 3 will be the same as the charge on 1. So this is going to be C3V3 equals C1V1. And this is simply C1 equals C3V3 over V1. So 0.8 times 10 to the minus 6 times 5 over 2. You know, whatever that happens to be. Okay, so actually without a calculator, this is going to be 8 times 10 to the minus 7 times 5 over 2. 8 over 2 is 4. 4 times 2 is 20 times 10 to the minus, 7. That should have been a 7, which is going to equal 2 times 10 to the minus 6, which equals 2 microfarads. Okay. So there you go. That's sort of an example of kind of what happened in lecture and how it was represented on a test. Now, short answer question, you don't have to show all of these steps. You know, a short answer question, you just sort of state your final answer. So I think a lot of the times what takes a lot of time with full solutions is having to show all of your work, because that takes a lot of time. Also, full solution questions are just more involved. I think you will admit after looking at this question, there really isn't a lot of involvement. Really, all you're doing is you're doing C3V3 equals C2V2, and then C3V3 equals C1V1. That's not a lot of involvement. It's a little bit of involvement. That's why it's still a question, but it's not overly involved. And also, you don't have to show all of your steps. So you could like scribble in the margins, and it doesn't have to be very neat. The other funny thing I noticed, if you remember from chemistry, when you do solutions, you know, when you're diluting specifically, and you want to figure out what volume you need to dilute, in fact, that's actually very relevant in modern times right now, because I think you need at least it's like 70% alcohol to kill the coronavirus when you have like alcohol sprays, maybe 66%, I can't remember. So if you buy like really concentrated rubbing alcohol, that's like 99%, and you want to know how much volume to add to dilute it down to 70%, you know, you always do C1V1 equals C2V2, right? And this works on the conservation of moles. Conservation of moles means like if you have so many moles of you know, let's say alcohol, rubbing alcohol in your bottle, when you add water to it, it's the same number of moles of alcohol. It's just spread out among more water molecules. So adding more volume doesn't change how many alcohol particles are in the water. It just changes its concentration. The two equations look very similar. I mean, not only do they have the same symbols, they just mean different things. V is not volume, V is voltage, and C is not concentration, it's capacitance. But you know, the similarity of the symbols aside, the notion behind these two equations is very similar, right? Conservation of moles is the same as conservation of charge. You know, the charge on the plates has to be the same, whether you increase the voltage or play with the capacitance. You know, you already have so many charges on the plates. So if you play with the plates, the charges have to always be there. They can't go anywhere. Okay. Anyway, moving on. One last. Oh, I don't know what happened there. One last question. We will do before we move on is we also talked about finding the equivalent resistance or the equivalent capacitance. We talked about both of them yesterday. So let's do an example where we might do that. Again, we haven't really done a full-blown circuit analysis yet. We will do that today. So again, this is hooked up to some sort of imaginary circuit. We don't really know what the rest of the circuit looks like. That's okay. We don't really need to know what the rest of the circuit looks like to find an equivalent resistance. So we learned two rules yesterday. We learned the series rule and we learned parallel rule. So if we had to replace, how many resistors are here? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 resistors here. Let's say this is just cumbersome. Let's say our phone is such a small piece of hardware, we're not able to physically fit 9 resistors in the circuit. If we wanted to replace these 9 resistors with one resistor that has an equivalent resistance, what value of resistor should we be looking for? So that's the question here, find the equivalent resistance. So let's do that here. You have to take it sort of kind of like how you rearrange math equations, like bed math. There's an order of operations. You have to do one thing at a time. So here I noticed that the farthest in you can possibly go is not close to A and B. The farthest in you could possibly go are these guys here. So let's first simplify the thing that is most nitty-gritty, the thing that is most nested inside, and then we will slowly simplify and work from within outwards, and then that'll get us a simplified version. So these 3 here are all in series with one another. So the first simplification will allow us to obtain, oh, I put my dot in the wrong spot. Of course I did. Let's see here. What's going on? Oh, no, sorry. So this is R, 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 and there's this guy, R. But instead of writing the 3 resistors out here, the 3 resistors are in series with one another. So the way we combine the series resistor is we add all the resistances. So I'm going to replace these 3 with one resistor. And those 3 can be replaced with a resistor of equivalent resistance of 3 times R, 3 times the original resistance. Okay, so that's the first simplification. Now, the next layer to look for is, the current comes in, whatever, and right here it branches out this way and it branches out that way. So then we have to figure out that. So that's parallel, right? You see here that this R and this 3 are in parallel with one another. So the way we deal with parallel resistors is we combine them with inverses. So we say 1 over R equivalent is 1 over R1, in this case that's R, plus 1 over R2. R2 in this case is 3R. So when you combine them, this is going to be, let's see here, 3 over 3R plus 1 over 3R is going to equal 4 over 3R, and that's going to be 1 over R equivalent, which means the equivalent resistance is going to be 3R over 4, which coincidentally is actually less than R. Now, if you think about the implication of this, the equivalent resistance is less than 3R, and it's also less than R, which is kind of interesting. You're adding a resistor, but you're reducing the resistance. That just seems odd. It seems sort of counterintuitive. Well, let's think about, again, water flow. The analogy is water flow. Resistance in water flow would be having like large rocks or having a dam, in the river, preventing the flow of water. If you add a resistor in parallel, what you're doing is you're carving, like let's say you have a water stream and you have a dam. You have a dam here with a little bit of a hole in it. So you have just a little bit of water that flows through the dam. If you add a resistor in parallel, what you're doing is you're kind of creating a second channel, a second path for the water to flow through and get around the dam. So inherently, you're allowing more water to flow by adding a second channel. The second channel will have its own sort of resistance, whether it be a large resistance or a small resistance, but regardless of how big or small the resistance is of this new channel, you're still allowing more water to flow after having added the second channel compared to before adding the second channel. So overall, even though there's resistance in the new channel, overall there's less resistance in the circuit. That's the sort of conceptual logic of what's going on there. We'll revisit that shortly. Okay, anyway, so we have the equivalent resistance there. So my new circuit is going to look something like, oh, oops, too long of a, oh, I forgot there we go. So R, 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 and what do I have here? I have R, oh boy, that's a terrible R. I have R, this is 3 over 4R, and then we have another R. All right, and we are back to kind of the same idea we had before. These 3 resistors are in series once again, so we combine them by simply adding them together. So we would get A, B, R, 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 and then this guy would be 2.75 R, right? 2 plus 3/4, 2.75 R. If you want to use fractions, go nuts. And then the process repeats. Then again we are doing parallel as we did before, and then you'd be doing series as you did before, and you slowly sort of collapse the circuit one by one by one until you get one resistance at the end, and then that'll be your overall equivalent resistance. Okay, so there's a good review of some problems. Let's move on. So DC circuits. It's already 9:45, so we'll see how much we get through. So DC circuits. Now we're going to actually analyze a complete circuit from start to finish. So we're really, up until now, we've been really close at just tackling a whole circuit. So now we're finally there. You'll notice in a lot of textbooks, they use the chapter heading DC circuits. Well, what does it mean DC? Why can't we just say circuits? DC means direct current. Direct current means the current flow in the circuit is only one way. It doesn't oscillate, it doesn't go back and forth. It only travels in one direction, like a river. It only travels in one direction. That is different, or the alternate option instead of DC, something called AC, alternating current. And alternating current, we will talk about slightly later in the class, very briefly. It's not something we dwell on, but anyway. Alternating current is kind of what we use in modern society. Our wall plugs are alternating current. And that's where the electrons don't actually flow anywhere. They just sort of jiggle back and forth. And that's a way to sort of propagate another form of current. So we're going to be primarily focusing on direct current. So where did direct current come from? Unfortunately, it came from Thomas Edison. He was a proprietor in the early 1900s, late 1800s of direct current. And he pushed for this so hard. He was actually a businessman. Edison wasn't really a scientist. He was more a business guy. And direct current was actually quite dangerous. It had low voltages, but it had very high currents coming into the household. So if you ever, like by accident, electrocuted yourself because there was an exposed wire or whatever, it was quite dangerous. And Tesla, Nikola Tesla, the same scientist that the car is named after, he was actually the one that pioneered alternating current, and it was much safer at the time. He was able to have a very low current coming into the house, a high voltage, but a very low current. And the reason why it was safer is because voltage is not the thing that kills you; it's current that kills you. You know, when you have a static shock, when you get out of your car and you touch your metal handle and you get that little static shock, that static shock is thousands of volts. Right, you are sending an electrical current through the air. That takes a lot of voltage to do. However, the current, the number of charges that flow per unit time is quite small. It just means they're jumping. It's just like, this is going to sound very morbid, but that's like one person jumping off the Grand Canyon. That's a big potential. You're falling a long distance, but it's only one person, right? There isn't a lot of volume of people jumping. A high current and a high voltage is very dangerous. That would be, you know, like many things falling off of the Grand Canyon. One thing won't kill. Well, having one or two charges fall from a high voltage, it'll hurt your fingertip a little bit. But if it's only one or two, it's not that deadly. But a high current means a lot of charges are flowing, and that's what can kill you. So eventually, after Nikola Tesla sort of passed away, eventually his discoveries kind of took over, and the scientific community realized what he'd been doing all along. And now we have AC current in our household. Okay, so let's present the linkage between what we've learned in a previous chapter to what we need to study a circuit. So the linkage is actually Ohm's law. So here's an example. Assume that the voltage of the battery in the diagram below is 9 volts. And that the 3 resistors are known to be identical. So that means they have resistance R, R, R. What is the potential difference across each resistor? Okay, so this is part of analyzing a circuit, okay? What we do is we look at the net resistance first. We find the equivalent resistance first. So the way we do this is we look at, are they in series, are they in parallel, are they in a combination of series and parallel? If they are in a combination of series and parallel, we have to do it systematically like we did before. Luckily, this one's fairly easy. So what we do is we find an equivalent resistance, and the 3 of them are in series, so the net resistance is just simply 3R, and the voltage is 9 volts. So we see here that the current coming out of the battery is Ohm's law, V equals IR. So I said the trick here to analyze the circuit is Ohm's law. So we have a voltage of the battery, V, 9 volts. We have a net resistance of 3 times R, whatever R happens to be. So the current the current, oh, I guess the positive end of the battery is where we're claiming the current is coming out of. The current in this wire is going to be equal to V over R. And in this case, our net resistance is 3R, so V over 3R. Now, that's how much current is in the wire, V divided by 3R. They want to know, what is the voltage difference across each resistor? Well, now we look at Ohm's law for each individual resistor. We say V1 equals IR1, V2 equals IR2, V3 equals IR3. So like I said before, Ohm's law is really the key here to analyzing circuits. And the current in series resistors are all the same as one another, right? Because the current has nowhere to go. It doesn't branch. Whatever goes in has to come out. So it's not I1, I2, I3. It's just I in this case. So the voltage across resistor 1 is going to be I times R. Now R1, R2, R3, they could be different in theory. In this particular instance, they all happen to be the same. So this is going to be I was V over 3R times R. So this is going to be V over 3. And if you notice, they're all going to be V over 3 because they're all the same resistance. Now, you can see, though, in this equation, this is the same. This is the same in every scenario. If you had one resistor that had a higher resistance compared to another one, then it would have a higher voltage drop as a result. Same current in each resistor, but you can see here, if one resistor had a higher R value, it would have a higher voltage drop compared to its neighboring resistors. But since all the resistors here in the question are indicated to have the same potential difference, or the same resistance, they're all going to have the same voltage drop, specifically V over 3. V in this case is 9, so 9 over 3 is 3. So the answer is 3. Okay, this kind of revisits a notion I said not too long ago in this lecture. What happens to the voltage across resistor 4 when the switch is closed? So when the switch is open, current comes out of the positive end of the battery. If the switch is open, this is actually not part of the circuit because it's not closed. Current does not have the ability to flow through an open switch. So it goes straight through R1, and it branches through R2, and it branches through R4. So what is the premise? The premise is, well, originally there's going to be some number of amps that go through resistor 4. If we close the switch and add, what we're doing is we're actually reducing the overall resistance because we are adding that resistor in parallel. It's in parallel with resistors 3 and 4. So if we close the switch, we're actually reducing the overall resistance. So V equals IR. If we reduce the overall, let me draw the arrow perhaps in a different color. If we reduce the overall resistance, we are going to, and the voltage stays constant, right? Because the battery is the battery, it doesn't change. So if we reduce the overall resistance, we have to increase the current accordingly. Now the question though is, it increases the total current coming out of the battery, but what happens to the total current coming through this one? So here, what we do is we say, okay, the total current flowing through this network is what we have to figure out. So before we close the switch, while the switch is still open, we say the net resistance, R net, is, I guess it's going to be 1 over. While this is still open, then we have to first figure out the net resistance of this. So it's going to be 1 over R3 plus 1 over R4. And this is going to be, let's see here, R4 plus R3 over R3, R4. So that means this is going to be 1 over R equivalent, which means R equivalent is going to be R3, R4 over the sum of R3 plus R4. So that's how much resistance is in this network. And if we want to know the current, V equals IR. So the current in that network is going to be the potential difference from, let's say, this point to this point, divided by R equivalent. Okay, now, once we have the total current, we say how much current is actually going through 4. So how much current, current makes it through R4? Well, we know how much total current is coming into the network. It's V over REQ. So how much makes it through R4? Well, we say V equals I through R4 over, times R4. Well, the potential difference A to B of the whole network is going to be the same potential difference through R4. So these two voltages, oops, I drew the wrong arrow. These two voltages are the same. This is the voltage from A to B. This is also the voltage from A to B. That's the whole premise of a parallel resistor. And then we can see that the I value through resistor 4 is going to be VAB divided by R4. So that's how much current travels through R4 before the switch is closed. After the switch is closed, however, what's happening is the same amount of current before is now being divided up into 3 resistors instead of 2 resistors. So what we're saying here is you are now, you have a different amount of current coming in, and it's being split among 3 resistors instead of 2 resistors. So before we had only 2 options for the current, and then now we have 3 options for the current. That's like saying, if I had to think of an analogy, okay. If you live in a condo building, I suppose you may not be able to appreciate this analogy, but if you live in a house, perhaps you might. That's like saying you have indoor plumbing, you've got piping in your house. If someone is upstairs taking a shower and someone is downstairs, I don't know, running water in the kitchen sink, and somebody is outside, oops, grass is meant to be green. If someone is outside and they have like a little sprinkler here and they are watering their grass, if all the faucets in the house are on, there's going to be crappy water pressure, right? The person in the shower is going to be like, where's all the water? Why is it dripping? Why is it not like strong? It's because you have a limited supply of water coming into the house, and you're splitting that water between the shower, the dishwasher, the sink, the hose, and then each of those things are going to have a diminished amount of water flow. Same thing here. If you only have 2, like if the switch is open, there's only 2 here, all of the current coming in flows between R3 and R4. But if you close the circuit, that's like you're turning on, if you close this here, that's like you're also turning on the hose outside. And now you have, to split that water flow 3 ways instead of 2 ways. So that's sort of a conceptual understanding of why the current, the voltage across this goes down. Okay, anyway, moving on. Here, these are just a review of yesterday. We've done some we've done some worked examples using these equations before. So I don't want to dwell on them too much. They're just sort of there to remind you. We're going to need those equations here for this question here. So up until now, we've done some very rigid problems where they're neatly drawn with right angles and they're easily determined to be whether they're in series or parallel. So here, this is an example that's more indicative of real life. Like the wiring in your house is not done at right angles. The circuits in real life are not done neatly like we draw them in textbooks. They're sort of squee-haw, so to speak. So this is indicative of sort of a more real-life circuit, and I'll show you how you can sort of think and redraw a circuit to be more visibly appealing. Okay, so here, the figure shows 5 ohm resistors. So all the R values are 5 ohms. Find the equivalent resistance between points F and H. So we have resistance, we want to know the resistance between F and H. That means current is going to be coming in F and flowing out of H. B is find the resistance between 2 different points, F and G, but in due time. So if we come in at point F, we have 3 branches. We have this branch, we have this branch, and we have this branch. So if I had to redraw this to be more, I don't know, visibly appealing and easy to understand, I'm going to draw 3 branches, 1, 2, 3. In the top branch, I have 2 resistors in series. I have R and R. I have R and R. Okay, if I go through the middle branch, I just have R, and then I exit the middle branch. And then if I go through the bottom branch, I again have 2 resistors. And this is point H. So this diamond-shaped figure is just drawn in a convoluted way on purpose to show you that you can redraw them that are electrically equivalent, but are easier for our brain to sort of decipher. So here we can actually see how to simplify the circuit. So we go to the most in-depth part of the circuit first. So that would be something like dealing with these and then dealing with these. So we could, you know, do one simplification. So those 2 top resistors are in series with one another. So we add them. This is going to be 2R. The middle one stays R. And the bottom one, again, are the same as the top. They're in series, so we add them. And then now we see that there are simply 3 paths. Each path has 1 resistor. So the 3 resistors are in parallel with one another. So we simplify it one more time. And the way in which we simplify it, oh, I guess that's not G, sorry, that's H. The way we simplify is using the inverse, so 1 over REQ equals 1 over R, or 2R, plus 1 over R, plus 1 over 2R. And going through this math here, 1 over 2R, plus 2 over 2R, plus 1 over 2R. Everything now has the same denominator. You add everything, you're going to get 4 over 2R, which equals 2 over R. And all of that, of course, equals 1 over the resistance. So to find the net resistance, you say REQ is going to equal to R over 2. So if R happened to be 5, then R over 2 is 2.5. And you do something similar for part B. Instead of having the endpoint be H, you have the endpoint be G for part B. So that just means you have a different exit, which sort of changes how you draw your picture. Okay, moving on. Brightness. We all use light bulbs, and it's kind of fun to know what you're shopping for in the store. If you ever shop for a light bulb, you will have noticed that there is, you know, a wattage rating. Watts are measured, it's the unit for power. Now, you might go to the store and say, oh, this is a 30-watt bulb, a 60-watt bulb, a 100-watt bulb. Oh, I want the 100-watt bulb, you know, I want the best. Well, 100 watts is not necessarily the best. You know, it really depends on what you're needing the bulb for. So what is the wattage measure? You know, how do you interpret that number, you know, as a consumer, even as a scientist? So the way you interpret that number is brightness is directly a function of power. So if you want to compare the brightness of two bulbs, you compare their power consumption. So when you shop around and you see light bulbs at the store are rated for 60 watts, that means if you were to plug that light bulb into a standard North American household socket, given the wiring in your house, it will consume 60 watts of power. If I take that light bulb and I rig it up with a 9-volt battery and the light bulb, it's not going to consume 60 watts of power, right? Because the battery is a completely different electrical source than the AC current in our walls, right? So just because the light bulb is rated at 60 watts doesn't mean it's consuming 60 watts. If it's rated for 60 watts, it means if it's plugged in to a household circuit in North America that has 120 volts, it will consume 60 watts of power. That doesn't mean it always will. Also, just to sort of explain household circuits a little bit, the reason why when you plug things in, I can guarantee you it's going to give you 120 volts of power is because everything in your house is wired in parallel. When things are wired in parallel, if you remember, they all have the common start and common end point. So each plug in your house will be drawing a different amount of current. Obviously, some things have lamps plugged in, some things don't have anything plugged in. So the current through one plug might be 0, the current through another plug might be not 0. So the current in the different plugs is different, but the voltage, all the plugs are wired in parallel in your house, including your lights. That means the voltage across each plug will be 120 volts. That's how I can guarantee when I plug anything in any given circuit, it's guaranteed to be 120 volts. So anyway, this slide just says brightness if and only if power, pretty much. So this question, sorry, it's also a question on just the slide. So here we have a 100-watt bulb, we have a 60-watt bulb plugged into a 120 volt circuit like our house, and they're connected in two different ways as shown. So if light bulbs are connected in series with one another, the question is saying which one's going to glow brighter. And if you plug the same two light bulbs into parallel with one another, which one is going to glow brighter? So let's analyze that. I'm reminding you here what the power equations are. There's sort of 3 of them. So here we say if it's rated for a 60-watt power consumption, then that means you can actually calculate the resistance of that light bulb. The resistance of that light bulb is, well, P equals V squared over R. So rearrange for R, you're going to get V squared over power. So if it's rated for 60 watts, it means if it receives 120 volts of potential, then it will consume 60 watts of power. So in this case, I can find the resistance of the light bulb. I can also find the resistance of the 100-watt light bulb. The resistance is going to be whatever the resistance is, regardless of what circuit it's plugged into. The resistance is not a function of how much voltage it experiences. The resistance is not a function of whether it's in series or parallel. Okay, the resistance is an intrinsic property of the object. So I calculate the resistances. After I calculate the resistances, now I can simply analyze the circuits as they are. So in the first situation here, I don't know the voltage drop between the individual ones, right? Because, well, we just don't know it. We do know, however, it's the same current that goes through both of them because they're in series with one another. So I choose the power equation that does not have voltage in it because I don't know the voltage drop for the 60-watt versus the 100-watt, but I do know whatever the current is, which I also don't know, it's going to be the same. So I say here, okay, the power consumption for the 60 watt is I squared R60, and the power in this circuit here for the 100 watt bulb is going to be I squared times R100. Well, the I's are the same. So if you're comparing I squared R60 and you're comparing it with I squared R100, then the I's are the same. So we can sort of ignore the I's. And then we're just looking at the resistance values. The resistance value for R60 is going to be 120 squared over 60. The resistance value for the 100 watt is 120 squared over 100. Which one's going to have a higher resistance? Well, this denominator is smaller than this denominator. So smaller denominator means larger value. So in this case, the power rating, or the power that the 60 watt bulb receives is larger than the power of the 100 watt bulb, which seems very counterintuitive. You buy the 100 watt bulb because you think it's going to be brighter. But if you hook them up wrong, if you use them wrong, it won't be, right? I agree, if you buy a 100 watt bulb and a 60 watt bulb and you plug them into your house, which is wired appropriately, the 100 watt bulb will shine brighter because that's what it's designed to do. But that's only under certain conditions. If you wire these bulbs differently, i.e. if you wire them so they're in series with one another, then it turns out the 60 watt bulb will glow brighter. Now, spoiler, if we hook them up in parallel as they should be, then obviously the 100 watt bulb shines brighter, larger than the 60 watt bulb. Okay, so this is just an illustration of kind of how you can sort of use power to predict brightness, and hopefully gives you some insight into kind of how your house is wired. And when you're going shopping for light bulbs, whether they be LED bulbs or incandescent bulbs or fluorescent bulbs, it doesn't matter. The power rating is the power rating, and now you know what the power rating means. It's based on 120 volts, and we're assuming you're using them in parallel circuits. Okay. Here's another example. A light bulb is wired in series. So here's a light bulb. It's just a resistor. So here, a light bulb is wired in series with a 144 ohm resistor, and they are connected across a 120 volt power source. Could be like your house. Now, again, just to clarify, this is a DC power source. Your house is AC, so there's a little bit of a difference there. The power delivered to the light bulb is known to be 15 watts. I don't know how they could possibly know that, but let's just pretend that they do. What is the resistance of the light bulb? Note that there are two possible answers. So this is us analyzing a circuit. I told you at the beginning of this lecture that the key to analyzing the circuit is Ohm's law. So Ohm's law says V equals IR. I don't know what the voltage drop of the light bulb is, especially in addition to not knowing the voltage drop of the resistance simultaneously. The only thing that I know is that the voltage drop across both of them has to be 120 volts. That could be 20 and 100, it could be 10 and 110, it could be 60 and 60. I don't know how that 120 is divided up. I just know the sum of them has to be 120 volts. This is what motivates us to sort of combine the circuit. So we see here that they're in series with one another. So I can say that the equivalent resistance is R1 plus 144. I don't know what R1 is, that's obviously our goal, but the equivalent resistance is R1 plus 144. So I now get the equivalent circuit of R1 plus 144 and then 120. So I can see here that the current is going to be, or well, rather I should say, V equals I REQ, and this is going to be 120 equals I R1 plus 144. So we now know the current, well, as a function of R, but we now know the current that comes out of this battery. It's going to be 120 divided by R1 plus 144. All right, Now that I have current, where does that leave us? Okay, let's go back to the question. I've used 120. I've used 114. What I have not used is the power. Okay, so the power of the light bulb. How does that help me? Well, I do know power equals IV. Well, I don't have V. I do have power though, which is nice. I do have power. I sort of have I as a function of R, but I don't have V, which is a problem. So my unknowns here are I and R, and I have I as a function of R. So let's see if we can use a different rearrangement of the power equation that only has I and R in it. So if I scroll up a little bit, just to remind ourselves, this is the equation we need. It's a rearrangement of P equals IV. So it's P equals I squared R. So let's use that one. So it's also equal to I squared R. And we know I is going to be 120 over R1 plus 144 squared times R1. So we see here, if we were to expand, we get 15. I think that's the power, 15. Yeah, P equals 15. 15 is going to equal 120 squared R over R squared plus 2 times 144 R plus 144 squared, which is going to be 12 to the 4. Not that that matters. And then if you were to proceed to rearrange, you're going to get 15 R squared plus 30 times 144 R plus 144 equals 120 squared R. And if you rearrange, you're going to get 15 R squared plus 30 times 144 minus 120 squared R plus 144 is equal to 0. And this is a quadratic equation with A is 15, B is whatever that happens to be, and C equals 144. And you can solve the quadratic equation and then get your answer. And this is why the hint was saying, note that there are 2 possible answers. And that was sort of hinting to students that if you are getting a quadratic, you're on the right track. You know, we're helping you, give you that confidence. Now, I grabbed this question from a previous midterm. It wasn't my midterm, it was someone else's midterm. And, you know, I thought, I mean, it's a good example to use in lecture, but I also want to draw your attention to the fact that it's a pretty challenging question. It involves a lot of multiple steps. It involves using the quadratic equation, which is an equation that is, you know, often forgotten by a lot of students, and it's probably not going to be on any sort of physics formula sheet. And you know, most of the time when tests are done in person, you can't just go look up the equation for quadratic equation. So, you know, I objectively thought this question was actually fairly difficult to be on a midterm, and I have never put something on a midterm, you know, that's this involved, that needs this many sort of extra things from other courses. So anyway, it's good to do in lecture. It's just I'm telling you now, I would never put something like that on a test. Okay, now unfortunately, I have to make your lives a little bit more complicated. Not every circuit is easily refined. You know, we've done a few examples now where we find, let's say, the equivalent resistance or the equivalent capacitance, right? Not every circuit is able to be simplified. When is that not possible, you're thinking? Well, what if you, for instance, what if you have multiple voltage sources, like multiple batteries? In this example here, we have a battery down here in the bottom, and we have a battery here in the middle. Well, whether or not something is in series or parallel is really a function of whether or not they share a common point. You know, parallel means everything, all the branches have the same potential, right? That's the whole really notion of parallel. But here, you can't say that this is in parallel with this in parallel with this, because, you know, there's a battery here and there's a battery here. So the potential difference between G and E is different than the potential difference between A and D, because there's batteries. So you can't just combine them using your parallel and your series rules. When you are in a situation like this, you can't solve the circuit by simplifying. You still need Ohm's law, so that's still true. You still need Ohm's law. However, you need to get creative. And this is kind of where, and it's called Kirchhoff's rules. And if anyone who is listening in the class who is, you know, of some sort of Russian background, yes, I know I'm probably saying that name wrong. I think it's more like Kirchhoff, but whatever. I'm going to call it Kirchhoff. Kirchhoff is actually quite ingenious in that he pretty much devised a very, very simple but powerful toolbox, single-handedly, just simply based on intuition. And I just think it is absolutely brilliant. It really shows you the power of what you can accomplish when you just kind of take a step back and look at things kind of conceptually. So Kirchhoff came up with two main rules to analyze complicated arbitrary circuits. The first rule is called loop rule. Now, let me come straight out and say it. Loop rule is a fancy way of saying conservation of energy. Or more colloquial, what goes up must come down. Kirchhoff said, in a complicated circuit with many batteries, or even in normal circuits, loop rule is always true in simple circuits as well as complicated circuits. Kirchhoff said, at the end of the day, any closed loop has to use up all of the available voltage. Because if it didn't, if there existed a loop, a closed loop, and when I say a loop, I literally mean like a loop that you can trace with your fingers. You can literally trace it with your fingers, go, and then eventually you will come back to part of the circuit where you started from. Okay, I literally mean a loop, like literally a physical loop that is closed. Kirchhoff was saying the current that flows through any closed loop has to use up all of its voltage by the time it gets back home. The reason this has to be true is because, let's for instance, let me make this a little bit more concrete. Let me draw a closed loop here. Okay? If I was a charge and I was traveling along the lazy river doing my thing, every time I go through, let's say, a resistor, I lose a little bit of voltage. And I travel through this resistor, I lose a little bit more voltage. I go through this resistor, I lose a little bit more voltage. By the time I get back to the battery, the other side of the battery, the negative side of the battery, I need, it's a physical must. I need to have used up all of that voltage. Because if I didn't, if I came back to the negative end of that battery and I had, let's say, 1 volt left to spend, but I was a good little kid and I'm learning the value of money and I saved my money, let's say I saved some of my voltage. If I go through the battery, I gain another, let's say, 10 volts. Well, if I repeat my process, I already know I'm able to bank or to save, let's say, 1 volt. So, you know, if I start off at 0, I get 10, I go through here, I end off with 1 volt. Well, if I get payday and I get 10 more volts, then now I have 11 volts. And I go through and I spend 9 volts. Well, now I have 2 volts left. I get payday, so now I have 12 volts. Go through, spend 9. Now I have 3 left. Then I'm going to have 4 left. Then I'm going to have 5 left. Every loop I do, if I bank some of the voltage, every loop I do, I will continue to gain more and more voltage. And then with time, I will eventually have an infinite voltage, which doesn't make sense. Not only does it not make sense to have an infinite voltage, more fundamentally, it doesn't make sense to have a larger voltage than what the battery can provide. You know, eventually I will have more than 10 volts. That doesn't make any sense. The battery only is able to provide 10 volts. So, and again, further to that, eventually you'd have an infinite voltage, which is just demonstrably impossible. So Kirchhoff sort of realized this, and it falls back on a conservation of charge argument. That you cannot create energy, you cannot create charge from nothing, right? So whatever charge was there has to be used up and then reissued. So Kirchhoff said, loop rule, you pick any closed loop you want. The voltage drops in the loop must equal the voltage gains in the loop. Now, this is a very unfortunate way to live in real life. You know, if every day or every month you got paid and you immediately spent all of that money and you were left with literally 0 pennies the day before your next paycheck, that would be a terrible way to live. And unfortunately, there's a lot of people in the world that live that way, but that's a whole other separate deep topic I don't want to get into, but that's what it's analogous to. Physics is a not-for-profit charity. You know, physics does not bank any voltage for itself. It uses all the voltage it can because that's the way the laws of nature work. Charges at the end of the circuit must end up with 0 voltage. So in this example, Kirchhoff's loop rule, we have 3 possible loops in this example. So let me just kind of erase everything else here, and I will show you what I mean by there being 3 loops. So the first loop I already mentioned. The first loop is the left loop here. That's the first loop. The second loop, maybe I'll draw it in red. The second loop could be something like this one. And then the third loop, maybe green. The third loop would be the loop along the outside. Okay, so there's 3 different closed loop options humans could use to study the circuit. And you'll notice that there's a bunch of variables and a bunch of components. You will actually need to study every possible loop you can in order to have enough equations to solve for your system or to solve for the circuit. So what do I mean by voltage gains equals voltage losses? We will get to that momentarily. I want to finish kind of presenting Kirchhoff's laws. So Kirchhoff has another law, and I've actually sort of already mentioned this law, just I never gave it a name. He called it junction rule. And again, it's based on just simple intuition. What goes in must come out, right? If you have a current I that flows through one wire, and there is a junction or a split, a fork in the road, if you will, in the circuit, then the total current I has to be split up between you know, the current that goes down and then the current that goes to the right. Right? Like conservation of current. What goes in has to come out. If what goes in is I, then what comes out is I. But if there's 2 sources of out, you know, to the right and down, then the sum of those 2 currents has to equal I. I don't know what they are individually, but I know the sum of them has to be I. Those are the 2 Kirchhoff's laws. There's loop rule and junction rule. What goes up must come down. What goes in must come out. 2 very powerful but simple to understand concepts. And it is amazing what Kirchhoff's laws are able to do. So let's do an example. Which of the following equations is valid for the circuit below? Well, I've told you before, Ohm's law is how we analyze circuits. So let's see if we can figure out which of these is valid. Let's use, let's say, loop rule. If we use loop rule, we have 3 options for loops. Let's take this loop, for instance, the left loop. Well, we can start by going down, to the right, up, to the left. All right? So I've said with loop rule, voltage gains equals voltage losses. All right? What goes up must come down. Voltage gains must equal voltage losses. However far we step up, we must then step back down. Where are we stepping up? Here, we are traveling forward through a battery. We are gaining 2 volts. Okay. Trace, 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 trace. Okay, now I'm crossing resistor 1, or I guess resistor of resistance 1 ohm. If you travel forwards through a resistor, you are using up some of your voltage. You're using it up to maybe power a light bulb, turn on a fan, maybe a space heater. So that's a voltage loss. How much voltage do we lose? Ohm's law, V equals IR. So we are losing, what's the current? The current is I1, and this is going to be 1 ohm. That's a loss. Okay, we turn the corner. Now, when we turn the corner, you'll notice that it's a junction. We'll notice that because it's a junction, there will be a different current in this wire compared to the previous wire. So any resistor we encounter in this wire will have a different current in Ohm's law compared to the 1 ohm one we just did. Okay, we acknowledge that, we move on. We travel through a battery, but we don't travel forwards through a battery, we travel backwards through a battery. We're falling, we're going from the positive end of the battery to the negative end of the battery. We're falling down a hill. So that's actually a voltage loss of 4 volts. And we continue to travel this way through another resistor, and so that's another voltage loss of V equals IR. I in this case is I2, R is 2 ohms. Okay, turn the corner. When we turn the corner, we're back in the first wire. The first wire has current 1. However, that's inconsequential because there are no more resistors, and we come back home. That's what I mean by a complete loop. We started at the negative end of the battery, we end at the negative end of the battery. So here is the Kirchhoff equation for loop rule. Now, if I had to simplify a little bit, this would be 0 equals I1 plus 2I2, let's see here, plus 2. All right. Now, someone asked me yesterday, can you ever have a negative current? The answer is, well, my answer yesterday was current is a vector. So it's not so much that you can have a negative current, it's that you have a magnitude of current in a certain direction. You look at this equation and you tell me, is it possible for both I1 and I2 to both have the same sign? No. I1 and I2 cannot both be positive because then you would be adding 3 positive numbers to get 0. That doesn't make any sense. So either I1 or I2, or maybe both, have to be negative. This doesn't mean anything physical. It doesn't mean you have a negative current. It just means the direction of current that we assigned was wrong. Maybe in the group chat while I was answering this question, you were thinking to yourself, but Mark, how do you know the current in this wire is down? How do you know the current in this wire is up? I don't know. I guessed. Because ultimately, it doesn't matter. Ultimately, if I guessed wrong, I'm just going to get a negative answer. And then I know I guessed wrong. I just know it's in the opposite direction. That's the beautiful part about this process. That's the beautiful part of Kirchhoff's law. When you're analyzing the circuit, you don't actually need to know where, like, in which direction the current is in real life going, because the difference between current up and current down is just -1. So as long as you're internally consistent with your math, you'll solve for one of them, and then if it's negative, you know you guessed wrong. So that's the left loop. Let's do the right loop now. Okay, there's the right loop. So we're claiming current is up, current is this way, current is down, current is left. So voltage gains equals voltage losses again. Voltage gains equals voltage losses. So let's start somewhere. Maybe let's start here. Honestly, it doesn't even matter where you start. Personally, I like starting near a battery, but that's just, I don't know, my personal idiosyncrasy. We start from the negative end of the battery, we go to the positive end of the battery. That's a voltage gain, so that's going to be 6 volts. And we travel, and then we travel through this 3 ohm resistor. So we're traveling forward through a resistor, so it's going to be a voltage loss. So what we're doing is we're losing 3 times I3 volts. 3 ohms times current 3 volts, V equals IR. Turn the corner, we go up again, we lose 4 more volts, we lose 2I2, just like we did before. Now we turn the corner again and we're back in the original wire. So if we're back in the original wire, the current in the original wire is still I3. It's the same current up here, it's the same current through the battery, and it's the same current down here. And we are going through the 1 ohm resistor, so it's 1 times current 3. So this equation simplifies to 2 equals 4I3 plus 2I2, which is going to equal, I'm noticing here that everything is 0 on one side, so I'm going to pull everything over to 0. So 0 equals 2I3 plus I2 minus 2. So there's our second equation. And our third equation, our third loop, is the large one. And when you follow a loop, you have to pick a direction that you want to walk in the loop. So let's say I want to walk clockwise in the loop. So if I'm walking clockwise in the loop, I am, well, let's start next to a battery. Let's start here. I am traveling from the negative end of the battery to the positive end of the battery. Voltage gains equals voltage losses. That is a gain. Negative end of the battery to the positive end of the battery. That is like an escalator taking us up high. That's 6 volts as a gain. I lose 3 ohms times I3 volts, V equals IR. I go straight through the junction. Now, here's where things get fun, and this is why I'm doing an example with you. What's happening here is, when we set up our circuit, we guessed at the direction of the current. Here's what I mean when I say we have to be internally consistent. I don't know if I1 is actually down or not, but I assumed it was down in all of my previous analyses. So I still have to assume that the current, that's not working, okay. I still have to assume that the current is this way. If I am traversing, if I am walking, if I'm with my fingers, I'm sort of pulling along the wire, okay? I'm traversing my loop. What I'm doing is I'm going backwards through, maybe I'll do that in a different color. We are going backwards through a resistor, not forwards. Okay, here we were walking in this direction and the current was in this direction. When we walked through the 3 ohm resistor, we were like going with the flow. We were losing voltage over this resistor because we were walking in the same direction as the current. If we are walking upstream, then this is the bottom of the stream, this is the top of the stream. Meaning, if I go backwards through that 1 ohm resistor, it's actually a voltage gain. On the other side of that, I will have a higher voltage than when I started. So it's a gain. And then I continue going backwards. Here I'm at a battery, so we're walking from the positive end of the battery to the negative end of the battery, so that's a voltage loss. And then we're walking, and then we get back into the first wire that we started with. The first wire, we assume the current was traveling this way. So when we traverse through this resistor, we are actually going with the flow again. We're not going backwards anymore. We're no longer salmon swimming upstream. So it is back to being a voltage drop. So this is going to be 1 times I3, V equals IR, V equals IR, R being 1, I being I3. And then we simplify. So where does that leave us? That leaves us with 4 volts equals 3I3 plus, 4I3. 4I3 plus minus I1. So if we had to pull everything to one side, 0 equals 4I3 minus I1 minus 4. So that's how you would use Kirchhoff's laws to set up your loop rules. We've got 3 different loop rules. So we've got our 3 different equations. Let us now compare. Do any of these equations match what we have? So 2 minus I1 minus 2I2. I don't see that. I don't see that in any of our 3 equations. B, 2 minus 2I1. Do I have a minus 2I1 anywhere? No, I don't see that. C, 2 minus I1 minus 4 minus 2I2. Okay, well that's a little bit sneaky. 2 minus 4 is going to be negative 2. So really, I think I should be looking for negative, what would this be? This would be negative 2 minus I1 minus 2I2 is equal to 0. Everything's negative, so we may as well just make everything positive. So really, I should be looking for 2I2 plus I1 plus 2. Oh, that's this one here. Boom. Okay. Now, there's some psychology behind the question, of course. You might be thinking to yourself, well, Mark, that was a lot of work for a multiple choice question. You're right. If this was a full solution question, this is what I expected you to do, right? Set up all the loops, analyze them, show all your work. You have to understand the point of a multiple choice question. The multiple choice question, even though this would be a complicated question to do, to set it up my way and solving it my way, multiple choice question, you have one of these 5 answers is the answer. So instead of creating these, what you could do is you could just sort of test. You could just take A, for instance, and say, is there a loop that has voltage gains of 2 and, losses of minus I1 and 2I2? You could just systematically test each of the 5 answers. That is much easier to do. It is much faster to do. It is much simpler to do, and it involves less knowledge to do. Setting up the equations are much harder. Testing if the equations are valid is much easier. So, there's some psychology involved in these questions as well. Okay, how to approach solving circuits. So here's the overall sort of technique. First, label and assign the directions for the currents. You do not have to be correct, right? So step 1 here, this is me in yellow. This is me sort of assigning the direction for the currents. I don't know if I guessed correctly. Who cares? It doesn't matter. I'm telling you now, it doesn't matter. So step 1, label and assign directions for the currents. Label them as I1, I2, I3 to make sure that you stay organized when you're plugging them into junction or loop rule. 2, use loop rule to obtain as many equations as you can. Okay, so this is sort of an algorithm to solving circuits. Label all the currents. Use loop rule. If you have 3 loops, do loop rule for 3 loops. If you have 4 loops, do loop rule for 4 loops. Okay, that's step 2. Step 3, use junction rule. All right, we never did junction rule up here, so let's do junction rule really quickly. We see here, according to our diagram, current 1 comes together with current 3 and forms current 2. So junction rule says what goes in comes out. Well, what goes in is current 1 and current 3, and what comes out is current 2. So that would be junction rule. Simple as that. What goes in comes out. Current 1 and 3 come in, ergo current 2 comes out. So that would be another equation that helps relate things together. And then this is sort of a note. If you choose the wrong direction for current, no biggie, your answer will just be negative. All right, and this is another note. Kirchhoff's laws, meaning loop rule and junction rule, they're always valid. It doesn't matter whether it's a simple circuit that you could do easy. It doesn't matter if it's a hard circuit like we just did. It's always valid, okay? Because they're based on fundamental principles. Conservation of energy, always valid. Conservation of charge, always valid. Since junction and loop are based on conservation of charge and energy respectively, they're always true. So really, when you're doing your homework and solving circuits, there's really 3 steps you should be doing repeatedly, sort of algorithmically. And hopefully the more practice you have solving circuits, you'll realize that all the questions are really the same. It's just what makes them different is the combination of variables we ask for versus what we give you as givens, right? But the approach to analyze them are all the same. Label your current, set up your equations with loop rule and junction rule, and then algebraically solve. Now, one thing I guess I forgot to mention is within loop rule, you need Ohm's law. Oops, Ohm's law. As you've seen, we just did an example where we set it up, right? Okay, we're running short on time. Maybe on Tuesday, I'll try to come back and do some examples, but there's more material I want to get through. You actually have a tutorial today as well, later in the afternoon. So I have confidence that you will review sort of Kirchhoff's laws and electricity concepts in tutorial. So I feel comfortable, at least presently, skipping this example. And if need be, we can check in with you on Tuesday, but we can always come back to this example. There's also the solution here, so it's not that detrimental. Here we go. We will do this example though, because there is no solution posted, so let's do it. For the circuit shown below, what is the potential difference between point A and point B? So in order to know that, we first need to solve the circuit. So let's solve the circuit. So step 1 is to assign a direction. If you recall, let's scroll up. Step 1 to solving the circuit is label and assign directions for the current. And then step 2 is loop rule, and step 3 is junction rule. So let's set up directions. I don't have to be correct. So I might use my intuition, but my intuition does not have to be correct here. What does my intuition tell me? My intuition says this battery is going to be pushing not electrons. It's going to be pushing positive charges, which we know now is not true, but whatever, is going to be pushing current this way. Okay, now there might be another battery in another part of the circuit that trumps that and like pushes it backwards, but whatever. Let's kind of see where my intuition goes with this. So if we call this current 1, then current 1 would come down here and then hit a junction. Now, this battery is facing this way. This battery will want to push current this way. this sort of fits with the flow of water, right? If you have water coming in here, it's going to want to push water this way and push water this way. That fits with this battery. This battery will help that sort of motion. So I'm pretty confident that current 1 is going to go down, current 3, oh boy, current 3 is going to go down, and current 2 is going to go to the left. That's what my gut tells me. Now, again, if your gut is wrong, who cares? When you solve, you're just going to get a negative sign. All right, I've labeled my currents. Step 1 is done. Let's do loop rule. We have 3 loops. We've got the top loop, the bottom loop, and then the perimeter loop. I just realized my battery's dying. 1 second. There we go. Okay. The top loop. So the top loop, I don't know, again, my idiosyncrasy is to start just to the other end of the battery. You don't have to, but whatever. So voltage gains equals voltage losses. So the gain right off the bat is 10 volts. And then I lose, come on, there we go. I lose V equals IR. So current 1, I1, R is 3 ohms. Turn the corner. The top loop, that means I turn this corner here. I immediately lose V equals IR, R, so 4I2. However, I go through a battery from the negative end of the battery to the positive end of the battery. So that's going to be another gain of 5 volts. However, then I walk forward through a 1 ohm resistor. So I'm going to be losing V equals I, R. Turn the corner. Now I'm back into current 1. Current 3 comes up here. Current 2 comes here, and then current 1 goes up again. And I turn the corner again, and then I travel through this. This is another loss of I1 times 2. So simplifying, I get 15V equals, let's see here, 3. Oh, not minus, sorry, it's a plus because it's already on the losses side. So 3 plus 2 is 5, 5I1 plus 5I2. Oh, well, that's convenient. So 3 is going to equal I1 plus I2. All right, that's handy. Okay, that's just one loop. That's my first equation. Let's say the bottom loop. The bottom loop, let me erase all of my scribbles. Okay, the bottom loop, we already know the current is traveling this way and this way, this way and this way. So my bottom loop is going to be a little bit interesting because in some fashion, we're going to have to go backwards through something. So let's say my loop is this way, hypothetically speaking. Voltage gains equals voltage losses. So again, my idiosyncrasy, I like starting next to a battery. Let's go forwards, follow the blue arrows. Let's go forwards through the battery. That's 5 volts. And then I immediately go forwards through a resistor. So I'm losing 1 ohm times I2. Turn the corner. Now I'm a salmon swimming upstream. If you follow the blue arrows, I'm having to walk upstream. The current is traveling clockwise, and I'm walking counterclockwise. I'm swimming upstream. So everything, like all the resistors, are then reversed. So here, if I travel backwards through the resistor, that's actually a voltage gain of 10I3. And then I walk back up this way, and I turn the corner, and I'm back on I2, and I2 is going to be a loss here, so it's 4I2. And then simplifying, I'm going to get 5 equals 5I2 minus 10 I3. And I can simplify this a little bit. I'm going to get 1 equals I2 minus 2 I3. Okay, so here's my second equation. Now I have a third loop, but I'm noticing I only really have 3 unknowns. I have I1, I2, and I3. I could solve for I3 using the third loop, but loop rule takes a little bit more work to set up. So I'm realizing I only need 1 more equation, and I'm going to use junction rule, because junction rule is fast and easy. So junction rule says we have I1 coming in, and it splits into I2 plus I3. So junction rule says I1 is going to equal I2 plus I3. Now we want to know the potential difference between point A and point B. That means I don't care about what happens in the bottom loop. I don't care about what happens in I3. So let's eliminate I3, because I don't care about I3. I3 is going to be I1 minus I2. And we can take this and plug it in. So this is going to be, well, there is no I3 in the first one, so that's fine. This means we're going to get 1 equals I2 minus 2 I3. I3 is I1 minus I2, which means we're going to get 1 equals I2 minus 2 I1 plus 2 I2, which is going to equal 3 I2 minus 2 I1 equals 1. All right, so this leaves us with 3 equals I1 plus I2, and 1 equals 3, oh no, we'll say minus 2 I1 plus 3 I2. And now we're just solving 2 equations, 2 unknowns. So you can use substitution, you can use elimination. It doesn't really matter to me. You know, if we multiply this equation by 2, we can get 6, 2, and 2. And then we could add them. So this is going to be 7 equals 0 plus 5I2. So I2 is going to equal 7 over 5 amps. The fact that we got a positive number for I2 means we guessed correctly. Once we have I2, we can go back and solve for I1. So any of the original equations, let's say we start with this one. So I2 is what, 7 over 5. So 3 equals I1 plus 7 over 5. I1 is going to equal 3 minus 7 over 5, which is going to be 15 minus 7 over 5. And 15 minus 7 is 8 over 5 amps. And again, we see that I1 is positive, which means we guessed correctly. Now that we have the current for I1 and I2, we're pretty much done. We want to know the voltage difference between point A and point B. All we do now is we go back and we say the voltage difference between A and B is going to be the voltage drop across this guy, the voltage drop across the 3 ohm resistor, plus the voltage drop across the 4 ohm resistor. So the voltage drop across the 3 ohm resistor is V equals IR. So it's going to be I1 times 3 ohms plus I2 times 4 ohms. And we know what these values are. I1 is 8 over 5. So it's going to be 8 over 5 times 3 ohms plus, and then current 2 is 7 over 5 times 4 ohms. And there you go. So 8 times 3 is 24. This is going to be 28 over 5. And then you can add them together. So that's going to be what, 52 over 5, which is going to be around 10. I mean, 50 over 5 is 10. So 52 over 5 is actually going to be 10.2 volts, I believe. 10.4, 10.4, 10.4 volts. So your answer there should be 10.4, I believe. So the answer is C. Okay. One last thing before I let you go. Normally when I teach this class in person, I actually print out this lecture slide and I hand it out to students, and I give you about 5 minutes to work on it, just because it's a fun little problem. I mean, I've never seen a circuit like this in real life. I can't even picture what in real life would represent this, but the complexity of this circuit in real life is nothing uncommon, right? Real life circuits in houses, in electronics, in your devices, the underground cables and your modems for the internet, like they're complicated, okay? And I just sort of, I like to hand this out to sort of show students the power of Kirchhoff's laws and how they can analyze such, very complicated circuits very simply. So here, look at how many batteries there are. There's the battery here, here, here. Like, you get the idea. There's batteries everywhere. And all the resistors here are the same. They're all 4 ohms. The question is, find the current that travels through that one very specific resistor. And this feels daunting. You can't simplify the circuit as we've done yesterday or this morning, because there's many batteries. So things are not necessarily in series and parallel. Now, you could sit here and do, set up your currents. You're gonna have many different currents, like 10, 20 of them or more, I don't know. You're gonna have loops coming out of every crevice of your body, like 50, 60, 70 loops, like this is a loop, like this is a loop, like there's so many different loops, okay? You'd be here forever. It would literally, you'd need a computer to do this in an automated fashion, okay? Humans, to do this the way I described algorithmically, humans couldn't do. This is what separates students who just sort of go through the motions and regurgitate kind of on a test. They would find these sorts of questions difficult. What brings you to the next level to really test to see if you actually fundamentally understand these concepts is seeing if you can sort of creatively apply what you know in new situations. So here, for instance, I'm giving you a hint. There is a loop that can get you the answer in a few seconds. So let me illustrate the problem with loop rule. We want the current through this here. So let's say we take a closed loop. Okay, that's one possibility. Voltage gains equals voltage losses. Okay, so here we would gain 4 volts. We would lose, now I don't know what current is in here. Let's call it current 1. So we would lose current 1 times R. This is a different wire segment, so we would lose current 2 times R. This is current 2. This is a third wire segment, so we would lose current 3 times R. I don't know what current 1, 2, and 3 are. So with loop rule, you're introducing more and more variables, which makes things complicated. So here, the key to think about is, in order to solve this, the problem is when you hit a resistor. Because when you hit a resistor, to figure out how much voltage loss you have, you need knowledge of current. If you hit a battery, you don't need knowledge of current, because you know the battery is 4 volts, regardless of whatever the current is. So the hint, there is a loop that gets you the answer in a few seconds that tells you avoid resistors. Can you find a loop that only consists of batteries? And now this is like one of those children's mazes on the back of a kid's menu at a Denny's, right? We've identified that we need a loop. We need to trace with our pen a closed loop that only has batteries. So, and specifically that one resistor, because that's what we want to know. So let's do that. Trace, if I go this way, I have to hit a resistor, I have to hit a resistor, I have to hit a resistor. So I can't go that way. If I go down, okay, I'm looking good so far. I can't go right because then I'll hit a resistor. So I have to go left. Can't go up because then I will hit a resistor. So I gotta go straight, I gotta go straight, I gotta go straight. Here we go, I go up through a battery, no problem. Battery, let's see here, battery, and there we go. There's that maze. There we go. So if we look at this, voltage gains equals voltage losses. I like to start next to a battery. So I don't know, just for fun, let's start here. Let's walk this way. So I'm walking forward through a battery. So I gain 4 volts. Oops, I gain 4 volts because the batteries are 4 volts. I keep walking, I go through another battery, 4 volts. I go through another battery, 4 volts. Keep going, keep going. I go backwards through a battery, so I lose 4 volts. And then I go through the resistor. So I lose current times R. What is R? R is 4. 4. So there's your equation. 4 and 4 cancel. So this leaves us with 8 equals 4I, which means I equals 2 amps. There you go. Okay, so naively approaching the circuit would be daunting. Kirchhoff not only allows us to sidestep circuit simplification, it's so fundamental and powerful that we can obtain an answer for this type of question very easily, without a lot of work, without a lot of time, without a calculator. I really think this is a beautiful, beautiful example of the power of Kirchhoff's laws. Okay, we are out of time. It's 11:05. We will quickly finish up RC circuits on Tuesday. It's a very small subchapter of electricity anyway, and honestly, for life science students, not very applicable. The only thing I would really mention in relation to life science students is an RC circuit is very similar to a defibrillator. I don't even know how to spell it. Defibrillator machine. I don't know how to spell it, so I don't really care. I'm not an English major. Maybe I should have been. But you know the things that shock people when they're dead and it jolts their heart awake. That is a defibrillator machine, and that is an RC circuit. So other than that application to life science students, it's not a major part of this course. It is a big part of physics. So if you're a physics major, that's a whole other story. But for this crop of students, it's not a main focus. So the fact that we're doing it next Tuesday, I don't see as being terribly detrimental. Okay, guys, thanks for coming out. I'm going to stop the recording now. So if you're watching on YouTube, I will see you on Tuesday. And I'm going to hang back for a few minutes to take some questions. Ciao for now.